In this video, we will discuss the central limit theorem. The central limit theorem: for all samples of the same size n with n greater than 30, sampling distributions of x bar can be approximated by a normal distribution with mean mu and standard deviation sigma over the square root of n. The figures below illustrate the central limit theorem. The original data, the figure on the left, is a histogram of the depths in kilometers of 1,392 earthquakes. And this histogram shows that those depths have a distribution that is clearly not normal. The sample means. The figure on the right is a histogram of 100 sample means. Each sample includes 59, I think that's supposed to be 50 earthquake depths in kilometers. And this histogram shows that the sample means have a distribution that is approximately normal. Given a population with any distribution has mean mu and a standard deviation sigma, and simple random samples all of the same size n are selected from the population. Practical rules for real applications involving a sample mean of x bar requirements. Population has a normal distribution, or n is less than 30. The mean, that should be greater than 30, not less than, I'm sorry. The mean of all values of x bar, the mu sub x bar is equal to mu. The standard deviation of all values of x bar, sigma sub x bar, is equal to sigma over the square root of n. And the z-score conversion of x bar is z equals x bar minus mu over sigma over the square root of, and again, that should be n. I'm sorry, I didn't proofread this better. Check the book if you have problems, or just listen to this because I corrected what that was supposed to be in voice, if not in the video. I'm sorry about that. Practical rules. Continued. Requirements. Original population is not normally distributed and n is less than or equal to 30. The distribution of x bar cannot be approximated well by a normal distribution, and the methods in this section do not apply. Use other methods such as non-parametric methods or bootstrapping methods. Considerations for practical problem solving. Check requirements. When working with the mean from a sample, verify that the normal distribution can be used by confirming that the original population has a normal distribution or the sample size is greater than 30. Individual value or mean from a sample. Determine whether you are using a normal distribution with a single value x or the mean x bar from a sample of n values. The individual value, when working with an individual value from a normally distributed population, use the methods discussed in section 6.2 with z equals x minus mu over sigma. If you're dealing with a mean for some sample of n values, be sure to use the value of sigma over the square root of n for the standard deviation of the sample means. So use z equals x bar minus mu over sigma over the square root of n. If all possible simple random samples of size n are selected from a population with mean mu and standard deviation sigma, the mean of all sample means is denoted by mu sub x bar, and the standard deviation of all sample means is denoted by sigma sub x bar. The mean of all values of x bar is mu sub x bar, which is mu, and the standard deviation of all values of x bar is sigma sub x bar, which is sigma over the square root of n. Note that sigma sub x bar is called the standard error of the mean and is sometimes denoted SEM. The elevator in the car rental building at San Francisco International Airport has a placard stating that the maximum capacity is 4,000 pounds or 27 passengers. Because 4,000 divided by 27 equals 148, this converts to a mean passenger weight of 148 pounds when the elevator is full. We will assume a worst-case scenario in which the elevator is filled with 27 adult males. Assume adult males have weights that are normally distributed with a mean of 189 pounds and a standard deviation of 39 pounds. Find the probability that one randomly selected male has a weight greater than 148 pounds. To do this, we use the methods presented in section 6 2 and seek the area of the green shaded region in the figure below. We convert the weight of x equals 148 pounds to the corresponding z-score of z equals negative 1.05. Referring to table A2, we find that the cumulative area to the left of z is negative 1.05, and that's 0.1469. So the green shaded region in the figure is 1-0.1469, sorry, the 1 minus 0.1469, which is 0.8531. That's our probability. The probability that the weight is greater than 148 pounds is a little more than 85%. B, find the probability that a sample of 27 randomly selected adult males has a mean weight greater than 148 pounds. Using the central limit theorem, because we are dealing with a mean of a sample of 27 males, not an individual male. Requirement check. We can use the normal distribution if the original population is normally distributed or n is greater than 30. The sample size is not greater than 30, but the original population of weights of males has a normal distribution. So samples of any size will yield means that are normally distributed. Because we are now dealing with a distribution of sample means, we must use the parameters mu sub x bar and sigma sub x bar, which are evaluated as follows. Mu sub x bar equals mu equals 189, and sigma sub x bar equals sigma over the square root of n, which is 39 over the square root of 27, which is 7.51. We want to find the green shaded area shown in the figure here. We convert the value of x bar equals 148 to the corresponding z-score of z equals negative 5.46 as shown here. Z equals x minus mu sub x bar over sigma sub x bar, which is 148 minus 189 over 39 over the square root of 27, which is negative 41 over 7.51, which is equal to negative 5.46. From table A2, we find that the cumulative area to the left of z equals negative 5.46 is 0.0001. So the green shaded area in the figure is 1 minus 0.0001, which is equal to 0.9999. We can be quite sure that 27 randomly selected adult males have a mean weight greater than 148 pounds. It is almost certain that the elevator will be overweight if it is filled with 27 randomly selected adult males. In the next example, we illustrate the type of thinking that is the basis for the procedure of hypothesis testing. It uses the rare event rule for inferential statistics, which we first saw in Chapter 4. Identifying significant results with probabilities, the rare event rule for inferential statistics. If, under a given assumption, the probability of a particular observed event is very small, and the observed event occurs significantly less than or significantly greater than what we typically expect with that assumption, we conclude that the assumption is probably not correct. Assume that the population of human body temperatures has a mean of 98.6 degrees Fahrenheit, as is commonly believed. Also assume that the population standard deviation is 0.62 degrees Fahrenheit. If a sample of size n equals 106 is randomly selected, find the probability of getting a mean of 98.2 degrees Fahrenheit or lower. We work under the assumption that the population of human body temperatures has a mean of 98.6 degrees Fahrenheit. We weren't given the distribution of the population, but because the sample size n equals 106 exceeds 30, we use the central limit theorem and conclude that the distribution of sample means is a normal distribution with these parameters. Mu sub x bar equals mu equals 98.6, and sigma sub x bar equals sigma over the square root of n equals 0.62 over the square root of 106, which is equal to 0.0602197. The figure below shows the shaded area, a tiny area in the left tail of the graph, corresponding to the probability we seek. We found the parameters that apply to the distribution, so we can find the shaded area by using the procedures discussed in section 6.2. We convert the score of x equals 98.2 degrees Fahrenheit to the corresponding z-score. Z equals x bar minus mu sub x bar over sigma sub x bar, which is equal to 98.20 minus 98.6 over 0.0602197, which is equal to negative 6.64. Referring to table A2 for values of 6 below negative values of z below negative 3.49, we use an area of 0.0001 for the cumulative left area up to z equals negative 3.49. We conclude that the shaded region in the figure is 0.0001. The result shows that if the mean of our body temperatures is really 98.6 degrees Fahrenheit, as we assumed, then there is an extremely small probability of getting a sample mean of 98.2 degrees Fahrenheit or lower when 106 subjects are randomly selected. University of Maryland researchers did obtain such a sample mean, and after confirming the sample is sound, there are two feasible explanations. First, the population mean really is 98.6 degrees Fahrenheit, and their sample represents a rare event, a chance event that is extremely rare. Or two, the population mean is actually lower than the assumed value of 98.6 degrees Fahrenheit, and so their sample is typical. Because the probability is so low, it is more reasonable to conclude that the population mean is lower than assumed. In reality, it appears that the true mean body temperature is closer to 98.2 degrees Fahrenheit. This is the type of reasoning used in hypothesis testing. For now, we should focus on the use of the central limit theorem for finding the probability of 0.0001, but we should also observe that this theorem will be used later in applying some more important concepts in statistics. In applying the central limit theorem, our use of sigma sub x bar equals sigma divided by the square root of n assumes that the population has infinitely many members. When we sample with replacement, the population is effectively infinite. When sampling without replacement from a finite population, we may need to adjust sigma sub x bar. Here is a common rule. When sampling without replacement and the sample size n is greater than 5% of the finite population size n, that is, n is greater than 0.05 n, adjust the standard deviation of sample mean sigma sub x bar by multiplying it by this finite population correction factor, the square root of capital N minus lowercase n divided by capital N minus 1. The samples and exercises in this section assume that the finite population correction factor does not apply because we are sampling with replacement, or the population is infinite, or the sample size doesn't exceed 5% of the population.